Here we'll talk about matrices and linear algebra. We'll start a video series on this topic here, and this is chapter 10 of Greenberg. In this video, I'll first give a brief introduction of the use of matrices, why we have them in the first place, and then most of the video will cover how to manipulate matrices with some simple operations, that is addition and multiplication. Then I'll get into some definitions, a definition of a transpose matrix, a diagonal matrix, as well as the identity matrix. After viewing this video and working through problems, you should keep this objective in mind, that is, you'll be able to add and multiply matrices of arbitrary form or size, and do the same with the matrix transposes as well as diagonal matrices. So recall that we had some experience with some general systems of M equations and N unknowns. And we looked at the linear algebraic form of this sort of equation, which looks like this. We have our coefficients associated with each of our N unknowns. The X's are our unknowns, and the A's being our coefficients. And we have N unknowns. And I've just written the first of our system of equations. The second of our system of equations would be written as such, with the first number again on the A coefficient representing the equation number, the second number of the subscript of A representing the coefficient of the unknown, the number of the unknown. And in general, we have M equations. And so what linear algebra allows us to do is to operate on large systems of equations like this in a very tight form. So using linear algebra, we could write the same system very simply as a matrix A times vector X is equal to vector C. And the overbar, I'm going to use the double overbars to denote matrices. And the single overbar for vectors. And I'd like you to do the same, because I want to make sure you know exactly the form of the variables that you'll be working with. And so linear algebra is a powerful system of ways to manipulate whole systems of equations. I should say manipulate and solve large systems of equations. And it's so widely used throughout the sciences. So this is a really important topic that if you pursue science it's likely that you'll see matrices and linear algebra in the future. So let's talk about let's define a matrix. And we've defined it again, but let's go over it one more time. So, or we can, well, really, so a matrix is it's a grid of numbers. The grid provides a way of organizing the numbers. And recall that the rows of the grid pertain to the number of equations being solved, and the number of columns of the grid pertain to the number of variables involved. So we can write a matrix in a couple of different ways. So we would write matrix A as such, and we would explicitly denote each element, the ijth element of A, as such. So, so the curly brackets denote the matrix, and Aij is not the matrix. Rather, it's the value of the ijth element. And so this is a definition. Each part of the grid is an element, and Aij is the ijth element. That is the element in row I, column J. If A is an m by n matrix, or I should say, if A has m rows and n columns, its form is m by n. Its form, or sometimes I'll refer to that as the size, but it's formally the form is m by n. So let's talk about matrix addition. Matrix addition is very simple. You just add each corresponding element. So we would write the addition of matrix A plus matrix B, for example, as matrix C. And we would define the sum. So the triple bars mean a definition as the ijth element of A plus the ijth element of B. Right? So that means that the ijth element of the sum is equal to the sum of those elements of the individual matrices. So that's relatively simple. So an example is if we had a 2 by 2 matrix, such as this. Let's call that A, for example. And our second matrix is another 2 by 2 matrix. Then the sum is 2 plus 1 is 3, 4 plus 2 is 6, 3 plus 1 is 4, and 4 plus 2 is 6. And you should notice that in order to perform this operation, A and B must be of the same form. And so, this is the requirement for the matrices to be conformable for addition. I'm using a different color, the yellow, to indicate a definition that you should know when working with matrices. So an example of two matrices that are not conformable to addition would be, for example, 2, 4, 3, 4 plus 1 and 1. This operation is undefined. We cannot add two matrices of different forms. So let's talk about multiplication. We'll get into multiplication here, but we'll first start with scalar multiplication. That is a multiplication of a matrix with a scalar constant. So C is our scalar number, and again we'll use capital A as our matrix. And the product of a scalar with a matrix is simply equal to the product of C times each element of the matrix. So, well, we can rewrite the product of C times the matrix as this, and the answer gives a matrix with element ij equaling the product of C times the element ij of matrix A. And I just want to be particular about what I mean by this notation. This means that, again, that the ijth element of the product C times A has the value C A sub ij. That's what this notation means.